Right.
Good.
Good evening from India. This morning we witnessed a brilliant session by Professor Alan Kafka from Boston College, who shared his reflections on the past 2 decades of his teaching, geoscience and public policy. The second lecture for today, that is the third day of IDWGST 2021, shall be presented by Dr. Daniela Kühn from NORSAR, Norway. NORSAR stands for Norwegian Seismic Array, which was established in 1968 as a part of the Norwegian-US agreement for the detection of earthquakes and nuclear explosions. So, Dr. Kühn is an extraordinary seismologist, and I had a wonderful opportunity to meet her in person during her visit to CSIR NES Jorhat. The topic of her lecture is Probabilistic Moment Tensor Inversion, examples from Europe. Before her session starts, may I request our session chairman, Professor J.R. Kyle, to say a few words. Over to Professor J.R. Kyle.
Thank you, Shantanu. Thank you so much. Warm welcome, Dr. Daniela Kühn. Your topic is so interesting topic. We all look forward to listening to you. So thank you again so much for accepting our humble request. And we are so happy to be with you this evening. Thank you so much. Please, Shantanu, please.
Thank you, sir. Now let me read out a brief biodata of Dr. Daniela Kühn. She is working as a senior researcher at NORSAR, Norway. She is also serving as a researcher at GFZ Potsdam, Germany, since 2015. The core research interests of Daniela include microseismicity, induced seismicity, moment tensor inversion of local and regional events, seismic hazard, ambient seismic noise analysis, waveform modeling, numerical fracture mechanics, amongst others. After completing her PhD from University of Hamburg, Germany in 2005, she pursued postdoctoral research at the same university for 2 years and thereafter at the NORSAR for another 2 years. Dr. Kühn published about 100 papers in reputed journals. I will conclude here and request Dr. Daniela to take over. Looking forward to an interactive participation from the attendees. Thank you. Over to Dr. Daniela.
Thank you, Shantanu. Okay, so I'll share my screen again. Did it work? Can you see the presentation?
No, not yet.
Not yet.
Okay. I'll try it this way. So now it should work, right?
Yep.
Yes, it is coming.
Good. Okay, so as already announced, the title of my talk is Probabilistic Moment Tensor Inversion, Examples from European Gas Fields. And I have a long list of contributors. So the first part of the list worked with me on events in the gas field in the North German basin, and the second part of the list on event in the Groningen gas field. But right now you may feel like this, so you most probably have heard about faulting since you are studying something with geophysics at least. You may have heard of earthquake source mechanisms. European gas fields probably depends on where you are living. Moment tensor inversion may get shadier, and what the heck is probabilistic moment tensor inversion? But what I will try to do is build the topics up one after each other. So I start out with some theory on faulting and earthquake source mechanisms. Then I come to moment tensor inversion in general and further explain the probabilistic part of it. Then I will change the subject slightly and come to human-induced seismicity and then apply both at the same time for European gas fields. So if we record a seismogram at a station, the seismogram will be influenced by several factors. It will be influenced by the characteristics of the receiver itself. It will be influenced by the medium the waves are traveling through, and of course it will be influenced by the earthquake source itself, and that is the part that we are now interested in. There are different fault types. So these three are the basic fault types. It's all shear faults, as usual for tectonic earthquakes. So on the top left, you see an example for a strike-slip fault that you obtain when two blocks slide horizontally with respect to each other. Then in the middle, you have a normal fault, and that you obtain if one block slides downwards with respect to the other. And at the bottom, there's an example for a reverse or thrust fault, which you get when one block slides upwards with respect to each other. So, but yeah, how to analyze now something like this? So what you can see here is a figure representing a shear fault right in the middle, and this is supposed to be a strike-slip fault. So the front part of the block slides to the left with respect to the back part. And you see different quadrants here. So in these quadrants here, due to the movement of these blocks, the material will be compressed. And if you put a seismic station up in one of these two blocks, what you will record is a positive first upward movement. The other two blocks, they are dilated instead due to the movement of the blocks. And if you place a station here, you will record a downward first movement. Yes, and that is now imaged in seismology in the following. So we imagine that we have a focus sphere and look at the earthquakes usually from below, and that has historic reasons, because in earlier times you would often analyze waves from teleseismic events that come from the other side of the globe. So you would, in a way, look at them from below. And in that, we now plot this fault plane. We also plot the second plane that is separating these quadrants, which is called auxiliary plane. And then we mark the positive and negative first onsets. And if we now plot these quadrants for the different onsets in black and white, we get such a shape, just a circle, and that is called Fokker mechanism, or often also a beach ball. But of course, usually you go the other way around. You have your stations and you record the movements, and you want to know what was the original earthquake source. So what you do now is that you take such a sphere again, and depending on the azimuth and distance to your stations, you now plot the movement of the first onset. If it was negative, like here for the station COL, or positive as for the station S or N, you do that for a lot of stations. The more the better. And then you try to fit this fault plane and auxiliary plane through these first onsets as best as possible. And of course, by now you don't do that by hand, but a computer does it for you and can also test different possibilities. And instead of just using this first motions or polarities, you can also use the amplitudes. That gives you even more information, since amplitudes will be smaller close to the nodal planes and larger in the middle of the quadrant. Or instead of using the amplitudes, you can also use the amplitudes of the full waveforms or parts thereof, like for example P or S phase. So this now depicts these Fokker mechanisms or beach ball for these three typical fault types. And if we now want to represent them in a more mathematical way, so such a computer can also understand, we use normally the concept of so-called equivalent body forces. And to represent such a motion here for such a strike-slip plane, for example, you need one so-called force couple at the fault plane and another one at the auxiliary plane. And you need a force couple so that you don't generate any net torques. And yeah, if you take only the force arrows now, you get that picture. And yes, so the mathematical description of such fold motion is done by so-called double couple forces. And these equivalent body forces will generate the same radiation as this fault. So they represent a source equivalent to the fault motion. One note, they do not describe the actual rupturing process in itself. That is much more complicated. So here are all force couples that you can think of for the 3 dimension of the room. And if we now want to describe these shear type faults I've shown you before, that are described by these 6 force couples. So every type of shear fault is described by a combination of 2 of those. And the different pairs are necessary to describe the potential orientations of fault planes and also the slip on these fault planes. And as you can see, these different pairs or parts of the pair will be symmetrical to each other. Otherwise, you again generate torque forces. And that has the implication that from only waveforms alone, we cannot differentiate what has been the fault plane and what has been the auxiliary plane. So additional information, for example, from geology is always required to do that. But then we also have 3 force coupled left here in the middle. So what are these for? And these are able to describe explosions and implosions. So for example, at the top here, you see a compressional fault. So you lose volume since both sides of the fault slide into each other in a way. And at the bottom is an example for an extensional fault. The other way around, here you gain volume because 2 parts of the fault move away from each other. So these middle force couples describe a volumetric change. And mathematically, the whole moment tensor can be described by a matrix tensor. So that is these with these 9 components. And as said before, it's a symmetric tensor. So some people also use just a vector with these 6 components. And just for comparing, so the fault plane solution or fault mechanisms, the beach boards I showed before, they only describe shear faulting. And mathematically, each of those is described by a double couple force pair. The moment tensor on the other side can also include a volume change. And usually it's split up for analysis into this volumetric part and the deviatoric moment tensor. And then the second part can be split up again, for example, into a best double couple. So that would then correspond to the shear faulting mechanism you see to the left, and a CLVD part, which contains the rest. And mathematically, this moment tensor is described by 9 force couples. And there are 2 things important to note. So first, this decomposition into volumetric and deviatoric moment tensor is also practical in case that you have a pure double couple sources, since noise in the data and also imperfect knowledge of the Earth, so you will never know it 100%, they will lead to artificial components, and for your interpretations that should be discarded. And this decomposition shown here in the second part is not unique. It can be performed in different ways, and that will also always lead to a slightly different interpretation. So what is the inversion part in the moment tensor inversion? That really describes the process that on the one hand you have the earthquake source that produces a wave that travels through a medium and are recorded as a receiver, and then the inversion you want to do it the other way around. So you have the waves that arrived at the receivers, you assume you know the medium they travel through, and you want to extract properties of the source. But now for the probabilistic moment tensor inversion, and that I will explain with the program that we commonly use, which is a Grant algorithm. Mathematically speaking, such a probabilistic moment tensor inversion is not an inversion. The inversion part is exchanged by forward modeling a lot of potential solutions. And that allows for application of a probabilistic methodology and, for example, for error estimation, which usually is not done in moment tensor inversion. So I'm showing here the homepage of the Pyrocco software, and this Grant algorithm is a part of the software, but this software also has a lot of different, very interesting packages for everyone who's working in seismology. And in addition to using the Grant moment tensor inversion, for the moment tensor inversion, you also need to view your seismograms. So there you have the snuffler. You also need to compute Green's function databases that will describe the wave propagation through the medium. There's a FOMOSTO package. And what's also always very nice is having a look at your velocity models and the rays within using the K package. I will show also an example of this later on. And here we have the homepage of the Grant algorithm. And very nice, here's a type-along introductory example. If you never heard of the software, don't know how to use it, it's very easy to just do this example. There are further example projects that are more complex, which you can also have a look on if you want to do the same with your data. And there's also a method section explaining in much more detail the process that I can now only touch upon. So for every such inversion, mathematically or not, you need the so-called objective function, and that describes the misfit between the data, which are here in the vector dops, and your synthetically forward computed waveforms, which are in the vector desynth. And the misfit in Grant is based on the LX norm, and the user can choose themselves if they want to use the L1, L2, L3 norm or whatever. So a first short digression on the topic of objective functions. What's an objective function? The objective function is a representation from the parameter space in which you search for the best solution. And depending on the formulation of your equations, you can either search for the minimum or the maximum. And shown here to the left is an example for an objective function where we search a maximum for locating a seismic event. So here, in that case, you have these 4 parameters that you want to optimize. You want to optimize the location in map view, y and x, and in the 2 depth sections, z and y, as well as z and x. And also you want to find the correct origin time, so the time t. And yeah, now we have a moment tensor inversion, not just an event location. So in addition to the location described by northing, easting, and depth, we also search for the magnitude and these 6 moment tensor components. So our space has already become more complex, not longer plottable in 3 dimensions. Therefore, we have these different slices here. So each of the forward models is, or the best forward model is represented by such a small dot. And the red dots indicate where the solution is better and the misfit lower, and the blue ones the other way around. And from that, we need to pick our best solution. Or better, the algorithm does it for you, luckily. And to arrive at a good objective function, it's important to weigh the data appropriately. And there are different parts to this weighting in the algorithm. So first, a balancing of amplitudes, which I will explain in the next slide. Then you can apply noise-based weight from your real noise before the first phase arrival to downweigh data that are very noisy. You can insert a manual weight for certain target groups, for example, P against S-wave amplitudes, since of course P-wave amplitude may carry more, as the same amount or even more information than your S-waves, but they are usually smaller. And finally, there are random weights for the Bayesian bootstrapping and the probabilistic algorithm that I will also explain in the following. And your final weight is a combination of all those different weights. To the balancing of amplitudes, so your signal amplitudes depend on the source receiver distance, the phase type, and the signal processing. And large signal amplitudes will always have a higher contribution to the misfit, but they might not necessarily have more information on the source mechanism. And to solve that problem, Hyman invented this adaptive station weighting algorithm, which enhances small amplitudes and suppresses large amplitudes in the objective function. And that is shown here to the left for the example of the resource receiver distance. So if you have your event here in the middle, of course, the stations that are close will usually have a much higher amplitude than the stations that are further apart. So in the objective function, you weigh them exactly the other way around. You upweigh or increase the amplitudes that are further away and decrease the amplitudes from station closer by. And then you need a good sampling scheme. So all the models are drawn from this large parameter space I just introduced, and the current best models with the lowest misfit, they are kept in a so-called high score list. And that allows the algorithm to efficiently converge to regions that have a low misfit while handling also multiple minima and compensate for eccentricity. And then in this probabilistic algorithm, you do not just solve one of these misfit functions or objective functions, but you solve multiple in parallel that are so-called bootstrap chains. Usually in an inversion run, maybe you run something like 100 of those. And each of these chains runs its own optimization, and they only differ by a random weight that is attached to each data point or target. So for example, here we have an example with 3 bootstrap chains. We have amplitudes, for example, p-wave amplitudes from 3 stations. The easiest is, of course, to weigh all these amplitudes similarly. And then here in the bootstrap chain 2 and 3, we attach random weights to those. And then on the right, that is plotted, these 3 bootstrap chains, they all try to converge to their own minima, which are marked by the stars here. And the n best models are then kept in this high score list for all the bootstrap chains at the same time. So, and then if you run the inversion, the search space will converge to these minima. And when the models in individual bootstrap chains, like the one in orange here and the other 2, become disjunct, further iterations of the inversion will not decrease the uncertainty, because the remaining uncertainty represents uncertainties of the models with respect to errors or noise in the data. So some examples here for data fitting. The one which is best known is the fitting of time traces. So these are shown here in the window, and with black is marked the observed time trace, and with pink the synthetic forward model time trace, and with red the synthetic time trace that has shifted a little bit, because we know that we don't know the velocity model very well. So we allow the algorithm to shift waveforms with respect to each other. The difference between both is shown at the bottom, and if I only want to deal with certain phases like P or S, I also use a taper window. And to the left, there's shown the station and component, the distance to the source and the azimuths, as well as the weight in the inversion and the remaining misfit. And instead of just inverting time traces, the algorithm also allows to invert different representation of time traces, like for example envelopes or absolute amplitudes, and also allows you not only to invert in time domain, but also frequency domain, so to invert amplitude spectra or even cross-correlation traces or even P2S amplitude ratios. So there's really a very high flexibility with respect to the type of input data. And we've seen this representation of the objective function before. And as mentioned, each of those points symbolizes a different source mechanism occurring at a different location and time. And what's plotted here are just the best 1,000 solutions. So for this inversion run in total, 6,400,000 models have been tested. There are also other plots that allow to explore the results. So for example, plotting of the mechanisms in space, so here in a map view, and to the right in a depth section with norsing, and the other depth section at the bottom. Another representation is also that from each inversion run you obtain a best mechanism and a mean mechanism, and if the inversion run was stable, then the best and mean mechanism should agree. If they differ, that's a sign for instability in your processing. So then coming to the topic of induced seismicity, there are cases where induced seismicity is intended, like for example when fracking or during fracking. So there you try to rupture the rock in order to better extract oil and gas. Or for the stimulation of geothermal reservoirs, there you also try to create a fracture network in the rock in order to either extract hot water, or if you have a dry hot reservoir, then to inject water, run it through the rock and extract it at another position while the water is heated up by the rock on the way. And of course, in that cases, you will create seismicity, but you know that. And there are also cases of unintended seismicity. So for example, during fluid injections of wastewater or CO2, in mines, at dams, in tunnels, and during oil and gas production. So there have been already quite some strong induced earthquakes, for example, during oil and gas production in the Wilmington oil field in California in the around 1950s, 60s. So there were several earthquakes due to dramatic subsidence of the oil field up to almost 9 meters. That's quite a lot. Or in the Ghazli gas field, Uzbekistan, there were 2 earthquakes with magnitude 7 in 1976 and 84, and up to this date, it's discussed if they were naturally or not. There have been a lot of earthquakes produced by injections. The first very known ones are in the Rocky Mountain Arsenal in Denver with magnitudes up to 5.5, but also in more recent times, similar earthquakes have occurred. Also, mining-induced earthquakes can be of similar magnitude, and at dams and water reservoir, usually induced earthquakes occur during the impoundment of the reservoir, but they can also occur due to seasonal changes. And also here we find earthquakes with magnitude larger than 6, for example in Koina in India, in Kariba in Zimbabwe, and in Kremasta in Greece. But also weak induced earthquakes can already be dangerous, since induced earthquakes usually occur at shallow depths, so also small magnitude earthquakes may cause damage. They occur close to expensive equipment, since by definition they occur during engineering operations. So for example, they can shear off boreholes. They are scary to population, since they often occur in otherwise aseismic areas, and they can be expensive. So for example, some costly examples are the Basel, Switzerland 2006 geothermal exploration that was stopped due to the occurrence of a magnitude 3.4 earthquakes, and that led to 2,300 claims for compensation. Then in Blackpool, Great Britain in 2011, due to a magnitude 1.5 and a magnitude 2.3 earthquake, extraction of shale gas was stopped for almost a year. And in Groningen in the Netherlands in 2012, a magnitude 3.6 earthquake led to 1,500 claims for compensation. And actually is a reason, or in general, seismicity in the Groningen field is a reason that the Netherlands will probably stop this gas exploration, at least in this field, completely. There's a very interesting publication by the Ellsworth and others from 2012 who observed a strong increase in earthquake rates for magnitudes larger than 3 in the mid-US. So what's shown here to the left is that from 1970 until 2000, earthquakes followed this red line here. So you had approximately 21 events per year with magnitudes larger than 3. Then between 2000 and 2005, suddenly the number of earthquakes began to increasing, follow this green line here. So you already observed 31 events per year with such magnitudes. And then it really became crazy. So from 2005 onwards, earthquakes started to follow this blue line here. So suddenly you had 151 events per year with magnitudes over 3 in the same area. And if you look on the map, all these earthquakes seem to cluster in very small regions. So there it was pretty clear that these were all human-induced due to coal bed methane extraction, oil and gas production, or also wastewater injections. And then I also want to explain shortly the difference between induced and triggered seismicity. So a lot of people only talk about induced seismicity, but in reality they mean both of these groups. So one definition according to Dahm et al. Is, for example, that triggered earthquakes usually occur on favorably oriented faults in agreement with the existing regional or local stress field. And only the event nucleation is controlled by the human-induced stress change, not the magnitude. So like shown here to the right in this plot, the triggered seismicity occurs on pre-existing faults, and human-induced stress changes only advance failure on this fault. So the fault would have failed naturally in the future anyway. On the left, there's an example for induced earthquakes, and these are entirely controlled by human-induced stress changes. They would not have occurred without the engineering operations. So I now come to my examples from Europe. So we are here in the North Central Europe region. The Groningen gas fields are in the Netherlands, more clearly here the northeastern part. And the Groningen gas field is one of the largest gas fields in the world and has been in production since 1963. On the right, you can see a plot of seismicity in northern Germany. There are some natural events and blasts, but there are also a lot of induced events marked by these yellow circles. And this part of the northern Germany is called the North German Basin, and that belongs to the federal country of Lower Saxony, which is one of the largest gas producers of Germany. And also here, the first fields have been in production since 1960. So for the Groningen gas field, the seismicity started in the early 1990s. So that's visible here on the left. The pink outline in the background is the size of the gas field, and all these small dots are earthquakes occurring between until 2014, and until December 2015, 900 events were registered, of which 256 exceeded local magnitudes of 1.5. And the largest event to date is a magnitude 3.6 event in 2012 that I mentioned before. And as you can see here from the histogram, most events have magnitudes around 1, but there's a fair share of events with magnitudes larger than 2 or even 3. And that's very scary to the population, since this part of the Netherlands is usually an aseismic area. In the North German gas fields, the events are marked here by the yellow circles, and here the gas fields are given with these blue polygons. So here you have several smaller gas fields, not this one large one. Nevertheless, if we plot the cumulative gas volume against the cumulative seismic moment, you can see that here also the number of events increased a lot in the recent years. And also magnitudes are not that low. So for example, in 2004, here in Rothenburg, we have a local magnitude 4.5 event. In Züge in 2005, there's a magnitude 3.8 event. And again, in Züge in 2014, a magnitude 3.2 event. And as Ellsworth showed in his publication, here's also, and also as a case for Groningen, we observe a delay between gas production onset of seismicity, approximately 20 years. And all this behavior looks very similar and suspicious. The instrumentation in the Groningen gas field is really very good. So by now there are more than 90 stations, and the waveforms are all online openly accessible in case you would like to play around with such a nice data set. And they consist of accelerometers, which are plotted here with yellow triangles, and by shallow borehole stations, which is plotted here by the turquoise triangles. So, and these borehole stations also always have an accelerometer at top, and then 4 geophones at 50 meter depths, 100 meter depths, 150 meter, and 200 meter. And due to this extensive instrumentation to analyze this event here, which is plotted by the red star, which occurred in March 2017 with a local magnitude of 2.1, it was sufficient just to use the station in a 10 meter radius around the event. We tried to use all level from each stations, but yeah, from some stations that was not possible. So only we chose really the best quality data for the inversion. The Langwedel gas field, in comparison, is much more sparsely instrumented, as you can see here. So that's an area of 30 by 30 kilometers. And there's an additional problem. So we have here 2 operators operating 2 networks, and the stations consist of 6 different types. So here, restitution of the data is absolutely crucial. So in our diagram, we are still on the receiver side. And a short digression, what is an instrument response function? Instrument response function describes the variation of sensitivity with which a seismometer reacts to ground movement. And that is in addition depending on frequency, as can be seen here in the diagram on the left, where different instrument response functions are plotted for several instrument types. And as you can see here, for the instrument, the broadband instrument plotted in the middle as well. For each instrument, that function differs, and for the broadband instrument, they are called broadband instruments because they stay stable over a broader frequency range. But still, also they are not recording all frequencies with the same sensitivity. In addition, from accelerometers, you usually get acceleration seismograms. From most modern seismometers, you get a record that is proportional to velocity. And if you now want to combine data that are recorded by different instrument types, all have in addition to removing the effects due to the instrument sensitivity, all have to be transferred to a common base. And for the Grand algorithm, or generally also for moment tensor inversion, commonly displacement is used. Here's also an example showing that with black, a short period instrument, with red, a broadband instrument, before restitution, they are at the same, they located the earthquake at the same place. So, but you can see that the waveforms they recorded look quite different. Only after restitution, so removing the instrument response function, both seismograms actually look similar. So then another example that now that you restituted your data, still you need to perform station quality checks. You cannot just assume that the data you have are correct. So still on the receiver side here. And for all the station quality checks I will show in the following, I use the AutoStats Q toolbox by Petersen et al. And here we did a test for verifying the station gain using power spectral density. So it's shown for a station to the left and a station to the right. And for each of the station, for 15 events, we plotted the modeled power spectral density in red and the observed power spectral density in black. And as you can see here for the green station, that fits very nicely. But for the red station, there's a problem. So the model sensitivity, modeled power spectral density is always lower. And that means you have an error in your station information. Another check that's worth doing is about the orientation of horizontal components. And for this, we use the Rayleigh wave polarization, again, for one station on the left and another one to the right, and for a whole lot of teleseismic events. And for station 1, we see what we want to see. So the maximum of this distribution here is around 0. So this is fine. But for the second station, for example, we see that for a lot of these events, the maximum is rather around 75 degrees. And that means you also have to apply this correction angle before using this data. A third check concerns the polarity of vertical components. And in order to check that, it's very helpful to use the PKP phase at a distance of 145 degrees, because here the amplitudes focus very nicely. So that means that you also obtain large amplitudes. So what's shown here is 2 different events, and then the vertical seismogram for different stations. And the PKP phase looks very similar for all of those. So here there's no problem at all. But just to show you how it can look, for this other network here, what we see is a PKP phase having a negative onset, and then suddenly for these 4 stations, a positive onset. So again, there's either a problem with your instrument or with the station information. If you do not have teleseismic event records, you can also use local events to check the P-wave polarization, or to use the P-wave polarization to check your component orientation. And that here is also an example from an algorithm that's included in the Grand moment tensor package. Another good way to use the power spectral density is to identify the frequency range for the inversion. So for example, in this case here, we looked at the waveforms and we decided we wanted to use for the inversion a range of 0.5 to 2 Hertz. And we decided to check that using noise recordings from a full day. And for all these noise recordings, we splitted them in hours and then computed the power spectral density. And there you can see it a little bit better here on the right. From a certain period on, all these amplitudes are only reproduced in one line. So this is a part of the frequency spectrum that you should not use. And then for the Lennard's 5 seconds instrument, which are a bit broader, the frequency range we chose was far outside of this range, so everything's fine. But then we also had some short period instruments. And then here, the frequency range 0.5 to 2 Hertz is right in the middle of this forbidden frequency range. So there, we had to choose a different frequency range and settled for 1.7 to 5 Hertz, which means for these different instrument types, despite the restitution, we still cannot use the same frequency range for inversion. And in general, I have to say, moment tensor inversion is not a one-step process. So also after carefully checking station quality, data quality, frequency bands, you always should test different velocity models, different station combinations, and different input data combinations. And at times that really feels like this, but in the end, you see it's more like this. So one example for testing input data combinations, still on the receiver side. What's plotted here are the results for different runs as fuzzy mechanisms. And what's a fuzzy mechanism? A fuzzy mechanism you obtain if you plot again your 1000 or how many ever results on top of each other. And if the inversion was unstable, you will only see such a gray cloud. If your inversion was stable and all these 1000 runs delivered the same result, then you will see such a clear separation in black and white areas in your solution. And what we tested here was for S phases and P phases used together in the inversion, use them as time traces, as amplitude spectra, as cross-correlation spectra, or different combinations thereof. And there were some runs that were much more stable than others. And from that, we also learned that more is not always better. So for example, in that case, it was very helpful to include S-wave amplitude spectra, but it was P-wave amplitude spectra had to be discarded. I'm not sure why, maybe they had a higher noise content or something. Here's an example for testing different station combinations in and excluding stations depending on uncertainty and orientation, on H over V peak, so the material below the station type. And from this we found out that it's good to include as many but high quality stations as possible. And for example, from the stations with the erroneous sensitivity in the station XML file that we discovered in our quality analysis, we should not include absolute amplitude information. So we included them only as cross-correlation traces. Then here are some examples for testing inversions using different velocity profiles. So we get closer to the source properties. We are in the medium now. And yeah, building a velocity model is always a challenge because there are two problems related to that. So first is that you need to know what the structure is of the subsurface and its properties. So depends on the data you have. And then the second problem is how to represent them in a model. So it's not an easy task to build a 3D model. And probably for this, most moment tensor inversions are still done using a 1D velocity model. But then how to represent such a case with a 1D velocity model? That's also not simple. So that is a section through the Groningen field velocity model, and it's quite complex, as you can see. Also here to the right, we have two sections, cross sections across the P-wave velocity model we obtained from industry, and there you can see that is not 1D at all. So what we did now is we tested the inversion using three different velocity models. So one, the NN model that is used by the seismological surveyors of the Netherlands for earthquake location. Then the KD model, which was used by previous publications for earthquake source mechanism inversion. And the N3D model, which we built ourselves. And we did that by averaging from a group of 1D velocity profiles that we extracted from the full 3D model. And as you can see here to the left, the NN model is the simplest one, so just a monotonously increasing velocity. The KD model in green looks already more complex with a low velocity zone here, but it still omits these two very high velocity zones that are part of the N3D model. And what are now the consequences of using different velocity models? For this, as I said before, it's very helpful to use a kind of ray tracing. So here we have the same source and receiver arrangement, but the three different velocity models. And there are 2 points now. So one, for a certain receiver and the different velocity model, the ray leaves the focus sphere at a different point. And if you do not acknowledge for that in your model, it will have an influence on your resulting focal mechanism or moment tensor. And then the second is that the wave paths through the different medias are of different lengths, and they also occur with different angles of incidence. And that means you get an influence on the waveform, both phases and amplitudes, which you also need to acknowledge in your modeling. So here we compare now results from the three different models in the three different columns and for three different stations in the 3 rows. And what we can see is that for both the NN model and the N3D model, actually the waveforms are fitted well in both velocity models, but the mechanism that you obtain is different. And what to do then? Then we look at other aspects of the solutions, for example, these earthquake location plots I've mentioned before, or also plots in the Hudson mechanism that gives a graphical view of the CLVD and also the isotropic component. But here in this case, I have to say we excluded the volumetric component from the inversion. So therefore the results cluster along the x-axis. And what we can see from those is that for the N3D model, we have significantly less variation in both location and mechanisms. So the solution is much more stable. And now we did the inversion for the full moment tensor, also including the volumetric component. We again look at these Hudson plots, and we can see from that again that also in this case the best solutions were very different. But for NN model and KD model, the solutions spread over very large areas in these Hudson plots. So on the one hand, that illustrates a spectrum of potential solutions, but it also indicates unreliability. Whereas for the N3D models, the solutions cluster very nicely again. So also here, that was our preferred solution. And if we interpret that, that is normal faulting with collapse with a normal faulting and collapse with a fault plane at reservoir level, which is very reasonable for the gas field where you extract a certain volume. Then we did a similar study for the North German Basin with a velocity model. So it's plotted here in a different way. We look at depth slices through the model from 360 meter depth to almost 5 kilometer depth. And what you can see is that the velocity varies a lot from shallow to deep layers, but it also varies a lot laterally. And indeed, here it was not sufficient to use such an average 1D velocity model for all stations. The inversion was still very unstable. So what we did instead is we extracted profiles at all station locations from the 3D model and grouped them by eye, and that left us with these 6 final velocity models. And here was also another thing that since station event distances are much larger in the North German Basin, so up to 30 kilometers for the stations that we use, waves also travel deeper in the subsurface. And we knew that the velocity model from the industry partner is only valid to approximately 4 kilometer depth. So what we did is combine these profiles at depth with refraction seismic profiles that luckily were also available. But we had to use different velocity models for different stations for this inversion. And that's the result for the North German Basin event. So in all cases, we obtained a slightly oblique normal faulting. The event depth was always within the reservoir. The fault strike is northwest to southeast, and the fault dips 75 degrees towards northeast, as you can see in the small sketch here. But what you can also see is that I still plot 3 different solutions here. So that were the last 3 inversion runs, and from those we cannot really say which one is better. And the location uncertainty is given by the vertical and horizontal bar. And the one thing we can see, which is good, is that our mechanism actually fits this longer fault here and also this short fault here from the fault model of the industry partners. So that's already fine and reassuring, but we cannot really tell if the events occurred on the longer or the shorter fault. That is just not resolvable with the network we have here. What was also not resolvable was a potential volumetric component. So I have some take-home messages for you. First one is on induced seismicity. So during most of the existence of our planet, earthquakes had natural causes, but within the last century, human undertakings, for example, mining, gas and oil extraction, filling of reservoir lakes, and so on, sufficiently influence the stress fields within the Earth to either cause or advance earthquakes. So that are these induced or triggered seismicity. And such earthquakes are often scary for the population and need to be analyzed. in the hope that we can avoid such earthquakes, which is an advantage, of course, with respect to natural earthquakes, which we cannot avoid. And also in contrast to natural earthquakes, usually described by shear faulting, such induced earthquakes often contain also such volumetric components. So then you need a moment tensor inversion to account for this. You cannot account for this by just a focal mechanism. To some take-home messages for the topic of moment tensor inversion is that faults, as well as their causes, the earthquake sources, can be described by mathematical concepts, in that case a moment tensor. And a full moment tensor describes the shear faulting, but also the volumetric part of the source. And earthquake wave records or seismograms are influenced by source properties, by properties of the propagation medium, and by receiver properties. And important, moment tensor inversion usually is not a one-step process, but requires testing. And a last take-home message with respect to the probabilistic moment tensor inversion that I showed using the Grond software package. It's a quite powerful and efficient algorithm. It allows for flexible input data. It has elaborate weighting algorithms. It effectively can explore the model space, also handling multiple minima and eccentricity. It provides a lot of plots that I find always very reassuring. And the advantage of a probabilistic methodology is that you get also uncertainties and therefore can account for parameter trade-offs. It's also easy to use. Well, maybe not that easy, but you as a scientist shouldn't have a problem. It's not a black box, so you can, it's an open source code. You can read through all lines of code, and you can even contribute yourself if you wish to do so. If you don't want to do that, still as a user, you have a lot of influence on the weighting of data, how you build your objective function, and how you search the model space. So with respect to the topics that I've listed at the beginning of my talk, I hope you now feel much better informed. And thank you very much for your attention.
Thank you, Daniela, for your nice presentation. Really a presentation with rich content. You have provided illustration on the moment tensor component and application of probabilistic moment tensor inversion in this seismicity. Now, may I request our session chairman, Professor J.R. Kyle, sir, for his remarks. Over to Professor J.R. Kyle.
Thank you, Shantanu. Thank you so much. I think we are overwhelmed, Dr. Kühn. You have made such a detailed explanation of right from faulting to fault-based solutions and then data quality and so on. It was so educative, so informative. Thank you so much. It was a wonderful, wonderful lecture we had. I have a few queries. One query is, at one place you have shown that induced earthquake, under the heading of induced earthquake, you have shown that Uzbekistan earthquake of magnitude 7. Could you please clarify? Could it be an induced earthquake or it is on a tectonic earthquake? Is it?
That is still discussed. Actually, there are several publications, and some authors are convinced that this is, well, as I showed afterwards, you can also make the distinction between an induced event and a triggered event. And these were probably not induced, they were too large for that. But they could still have been triggered by the gas exploration. So, yeah. And until today, that's unclear. And of course, I mean, that's a long time ago, so you do not have the seismic networks that we have today. So I also think the question probably will never be clarified to the end.
Dr. Kühn, my another query is that you have given us a very detailed information on the moment tensor solution. Now, in doing so, you have also given us understanding that it also how much the velocity structure can influence the moment tensor solution. So my just simple query as a layman, you can say, whether if we have enough fast motion data, whether fast motion solution is more stable than a moment tensor solution in a complex velocity or a very heterogeneous terrain in I mean tectonic zone. What is your opinion about that?
So I would say if you have an excellent information, so if you have a really good velocity model and you have a lot of high quality stations, then also your moment tensor solution should be stable, as was the case for the Groningen field, where we know really the velocity structure very well and they have this extensive instrumentation. But if you either your information on the velocity model is not that good, or you have less stations, as was the case, for example, for the North German gas field, then the full moment tensor becomes more difficult to derive. But then, in my experience, it's still better to go for a deviatoric tensor than just the focal mechanism. Because if you only derive the focal mechanism, so really you assume that you have a shear fault, then all errors in your data and the noise will be mirrored in the position of the fault planes. Whereas if you choose a deviatoric mechanism, usually you get a very nice solution for the shear fault, and the noise is in the deviatoric part where you are not so interested in anyway. So I would, I would recommend still doing a moment tensor inversion and with a deviatoric.
Thank you so much. It was so interesting. Thank you so much. Over to Santanu.
Thank you, sir. So, sir, we have one special guest. He is Professor Mohammad Farouk from National Research Institute of Astronomy and Geophysics, Egypt. So, Professor Farouk, if you have any query, you may please go ahead. Over to Professor Farouk.
Yes. Okay, I have some questions. Thank you for this nice lecture. I have some questions regarding the method that you are using. First of all, you have discussed that you should have a very detailed crystal model. That means I have to know my 3D model exactly to solve the focal mechanism or the MTI. However, this is one of the most difficult thing to have, because actually we have the problem of the source. This is the main target. So the most difficult thing is that the model that you are using. So the model should not be so sensitive. The method should not be so sensitive for the velocity model. Otherwise, we will have different solution. Okay, this is my first. I want to see your comment about this. Please.
Yeah, I think it's not so much a question of the algorithm actually. So also I've used a very robust focal mechanism computation. And if your medium becomes too complex, like in a mine where you can have cavities, then every algorithm struggles. So that's the first point. The second point is that the examples I've shown here now for the velocity model, they are also extreme, because both in the North Netherlands as also in the North Germany, you have these salt diapirs coming up, and that is a complex structure. So also other algorithms will have problems with it. In a lot of parts of the world, you get away with a stable solution with a 1D velocity model. It really depends where you are. I mean, yeah. Okay. And it also depends, of course, on the size of your events that you analyze. Since, I mean, if you have a magnitude 7 earthquakes, then you can use much longer frequencies and stations that are further away. And then your velocity model becomes less and less important. That's a problem in general with this induced seismicity. Since magnitudes are lower, you use usually local or regional networks, and you need to use the data at high frequencies, either because your magnitudes are low, or also because your sensors just, if you just have a short period sensor, you cannot use long period waves. And then if you use higher frequencies, then you need to know the velocity model in more and more detail. So it really depends on your situation as well.
Yes. So this comes to the question of the speed of your algorithm. If you use a high frequency and the 3D model, so I think you need much more time for computation. So what is the speed of your algorithm for solving this?
Also the example I've shown here, which used these 100 bootstrap change and which resulted in these over 6 million forward computations, was done in an hour.
1 hour?
Yeah.
Oh, good. It's good. It's a good time.
Yeah,
Okay,
the developer of the code, he really thinks a lot also on hardware requirements. So when he drafted the algorithm, he really thought on how is data physically saved on a hard disk and things like that. So it's very efficiently in computation.
So I'm sorry again. You're using your synthetic. The comparison between observation and synthetic seismograms are done in frequency domain or time domain, because it may be different. I don't know. Understand?
No. Can you repeat?
When comparing the observed seismogram with the synthetic seismogram for the best fit, you are using the frequency domain or time domain in this comparison?
Both. So we used time traces in the time domain, and we also used the amplitude spectra computed in the frequency domain.
Okay.
So we combined both. And in addition, we also used cross-correlation traces. So these are not helpful if you want to derive the magnitude, that it has to be taken from the frequency and time domain, but they are very helpful in fitting the phases of two wave trains. Okay,
the magnitude value of the earthquake should be known as an input value or not necessary?
Sorry, I did not understand.
Magnitude of the earthquake that I am using should be known or not needed?
No, the magnitude is also computed by the algorithm, as well as the location.
Okay, that's very nice. So, according to your opinion, what is the limitation of this method if someone wants to use? What's the limitation? For example, the minimum magnitude that is calculated and something like this.
The limitation is the magnitude of events, since if you have very low magnitude, as first you will have less stations recording that event. So I would always recommend, if you want to compute a moment tensor or also focal mechanism, you need a nice azimuthal distribution of stations. And it's also good to have stations at different distances. So if you just have a magnitude 1 event, you only will have few stations that record it depending on your network. And the second limitation with low magnitude events is that then the frequency content of the seismograms becomes higher and higher, and then you need to more and more information on your velocity model.
Yes, I think that's all. I think thank you very much. Okay.
Thank you.
Thank you. I think Daniela, we can take some questions from the attendees.
Sure.
Yeah. Over to Mr. Prasudha Bhattakur. Over to Prasudha for question and answer session.
Sure, sir.
Yeah. Go ahead. Yeah.
Thank you, ma'am, for such an informative talk. With your permission, I am going to read out the questions from the participants across the globe. So the first question is, does stationarity of hypocentral parameters plays an important hypothetical standard for probabilistic moment tensor inversion?
What? Can you repeat the first part?
Does stationarity of hypocentral parameters plays an prominent?
That is a centroid moment tensor algorithm. So it will, yeah. So the hypocenter gives a point where the rupture starts, and the centroid gives a point where the largest energy is released. And that is yes. So So there's no kind of stability in that case. So also if you have an extended rupture where rupture will propagate over the fault, with this moment tensor, you will get the result for the maximum energy release. So it does not matter if you have different slip around.
Okay, ma'am. The next question is, why sometimes there occur all the three types of solutions? Why is it so?
They will not occur simultaneously. It's just different cases that may occur in different regions.
Okay, sure, ma'am. The next question is, does probabilistic inversion can be applied to determine earthquake mechanism and source time function for weak events epicentral distance less than 100 kilometers?
Yeah, in principle, that's what we did in these gas fields, in the Groningen gas field and also in the North German basin. So the distances were, for the Groningen gas field, we used just 10 kilometers, and for the other, it was like 30 kilometers. We did not try to derive any source time function. And yeah, as I never tried it with this algorithm, I don't think you can. Maybe you could. Since you can always contribute to the code. So.
Thank you, ma'am. There are a lot of questions. Due to the time restriction, we are going to email the remaining questions. Thank you, ma'am.
Sure.
Over to Dr. Santanu.
Thank you, Pasija. Now, may I request Nabajyoti Molia for computer science? Over to Nabajyoti Molia.
Excuse me, Dr. Shantanu. Hello, Dr. Shantanu. Before going for the vote of thanks, if you can kindly allow me to ask a small question.
Yes, go ahead, please.
Okay, Dr. Kühn, am I audible?
Yes.
Yeah,
Dr. Kühn, first of all, I would like to extend my heartiest congratulations to you for such an elaborate and a very lucid presentation, which was intelligible to everybody. My question is very simple. What I understood is that your final conclusion was that in the oil and gas industry, where you have conducted your experiments, you have come out with a normal solution which is slightly oblique and volumetric changes. These are the two main findings. So, what is your home take message that you would like to give to the industry people operating in that region? So, for any kind of remedial suggestions or something like that, would you like to come out for the oil and gas industry operating in that area? What is the home take message for the oil and gas industry?
So for the project in the Groningen field, we actually worked with the industry partners that are exploring the gas fields, and they were very interested in the source mechanisms, since they run a very high quality and complex reservoir model for the region. And from this, they compute the seismic hazard and risk. So for them, having the source mechanism as extra input reduced a lot of the uncertainty in the hazard computations. So then my take-home message would be that for all industry partners running such an operation, it's helpful to install at least some seismic sensors. Because it's not only an annoyance, it also helps.
Thank you so much for addressing my question.
Sure.
Bye-bye. Goodbye.
Thank you, Dr. Soduri and Dr. Daniela. Now, may I request...
Sir, I have a question.
Molia?
Sir, excuse me, sir. Excuse me, sir, I have a question. So, can I proceed? Hello, sir.
Go ahead, please.
Yes, please, you carry on.
Okay, sir, thank you, sir. Sir, I have a query. So, ma'am, what are the actual applications of MW, or how can we use MW in AI?
NW?
In AI, I mean artificial intelligence.
Ah.
How can we use this Fokker mechanism solutions results or MW solutions in AI?
Well, maybe rather the other way around. How can AI be used for moment tensor inversion? I'm sure it probably can. I have not tried it, so I don't know. What I know is that usually a lot of experience is also needed. So there are some decisions. So for example, also I try to test different station combinations and other combinations, but I need to look at the results to decide, okay, from what I know from geology or something else, I prefer this solution. And there, I would be interested to see how good an AI can do that. I don't know,
Yes.
but if it really can have this level of professional experience.
Thank you, ma'am. Thank you.
Sure.
Thank you.
Yeah.
Namazati, please go ahead.
Thank you, sir. A warm good evening to all from the lane of unity in diversity. As today's event has come to an end, it is my pleasure to convey hearty thanks to everyone on behalf of entire CSIR NIST family and organizing committee of IBWGST 2021. I take this opportunity on behalf of entire CSI NIST family to thank Dr. Daniela Kühn, NORSAR, Norway, for promptly accepting our invitation with anticipation and delivering today's lecture on probabilistic moment tensor inversion examples from Europe. Once again, a hearty thanks to Dr. Kühn for sharing momentous information on probabilistic moment tensor inversion. I further convey my sincere thanks to Director Dr. G. Norhari Sasti of CSI NIST Jorhat for his immense concern and implication to successfully organize the live session meets. Sir, once again, hearty regards. Our heartfelt thanks goes to esteemed international advisor of this workshop, Dr. Andrzej Michael from USGS, and session advisor, Professor Daping Zhao from Tohoku University, Japan, for their constant vision and support for the event to be a grand success. I would also like to thank the session chairperson, Professor J.R. Kyle, former DDG of GSI GovTop India, and co-chairperson Dr. Saurabh Barua sir, Chief Scientist CSIR NIST, for their diligent commitment towards the event to be successful. I would also like to thank a special guest of today's session, Professor Mohammad Farooq from NRI AZ, for his gracious presence. Once again, I take the opportunity to thank Dr. Santanu Barua, convener of this workshop, for his vigorous devotion for this international live session meets. We once again sincerely thank him a lot for bestowing his opportunity to unite laureates from different regions of the world under a single online podium. Last but foremost, I express my sincere thanks to all the attendees for their active involvement in today's event, without which this event would not have been a success. We, with anticipation, are also looking forward for tomorrow's session sharply at 10 a.m. Indian Standard Time. The speaker for tomorrow's session is Honorable Professor Daping Zhao from Tohoku University, Japan. He will deliver a talk on seismic anisotropy tomography, new insight into seismotectonics, volcanism, and geodynamics. With this, I conclude this session. Namaskar Hokololoke with hearty love from Assam. Thank you, ma'am. Thank you, everyone.
Thank you so much. Thank you.
Bye.
Have a nice time.
Thank you for having me.